Okay, got it. Okay, so I wanted to do this introductory talk where I will talk about what I did in the thesis, some parts of what I did. And so let's start, if it works. Okay, let's start with the outline. I will give you a very brief introduction to what modified gravity is and why we want to explore this. Then I will give you a brief example of how to constrain this modified gravity with models, with data, sorry, with a very simple model. And then I'll turn my attention to some model-independent approaches to modified gravity. And in the end, I'll draw some conclusions. So if we want to summarize things a lot, the standard model of cosmology is mainly based on two principles, let's say two assumptions. One is the cosmological principle. So we have that at sufficiently large scale, the matter distribution is homogeneous and isotropic. And the main consequence of this is that we can use the three-dimensional matrix or the sum-Walker metric that we always use in cosmology. But then there is another more mathematical assumption that is at a large scale, we use the general relativity equations, where we add the part related to the fact that we know that the universe is expanding, accelerating. So we use to model this cosmological constant. But we know from experiment that the cosmological principle is very well tested. So what we might want to change are these equations here. So the general relativity equation. The question here is, why do we want to do that? We already have this model with this object here that is modeling the acceleration of the universe really well. Well, if we try to give an interpretation of what the cosmological constant is, we know from the equation of motion that a cosmological constant means a constant energy density for the part related to that. And this means that we might be tempted to use a quantum field theory interpretation of what the cosmological constant means. And if we do that, we can interpret it as the energy of the vacuum. And doing the calculation with quantum field theory, with up to some cutoff, that is the Planck mass here, we find this value here. But the main issue about this interpretation is that if we look at the value in cosmology, we find a value that is something like this, that is 120 significant digit different. And this means that there must be some kind of screening mechanism that is screening this value in order to give us this other value when we do the observations in cosmology. And this is why sometimes this is called one of the worst theoretical predictions ever in physics. And this at least may give an hint why we want to explore some alternatives to standard general relativity and cosmology. And the main way to do that is to consider the equation of motion and just try to substitute the part related to the cosmological constant with a tensor that is a very general one. So it might include new degrees of freedom. Or in a more general way, what we actually do is to modify the Lagrangian, so the Aston-Hilbert action, with something that depends non-trivially on the Ricci scalar, but also other curvature tensors, and new degrees of freedom that can be scalar, vector, tensor, but also there might be some non-standard coupling between the matter and these new degrees of freedom. So we have a lot of freedom to choose this function here. And it seems simple in the sense that with this, we can have an infinite freedom how to choose this function, then model whatever we want. But actually, this is not the case because we have always to deal with experimental data. And what we have to do when we propose a new modified gravity model is to check, firstly, the background equations. So we assume that the cosmological principle is valid and everything is only time dependent. And we check that everything is consistent with the observation we have, for example, the age of the universe. But then this is not enough because we know that the cosmological principle is not valid at smaller scales. So we have some perturbations around the background that gives us the first order perturbation theory, for instance, in the CMB. And we have to check that our modified gravity model actually is consistent with the data that we have from the CMB spectrum. So for instance, the data from Planck. And then we have also to check similarly the nonlinear structure formation, because obviously our modified gravity model might also change that part. And in principle, we have also to check other things. For instance, that in the solar system limit, we have that our model is valid. So it gives us consistent result with what we know from experiments. And then there is black hole formations in our modified gravity model, and also that the gravitational wave speed that we know from LIGO vehicle to be equal to the speed of light approximately, up to the error that they found. And this is not an exhaustive list of what we have to check when we consider a modified gravity model. But let me give an example of how we can do this, constrain the model with some data. Okay, here you see a model that is called Pneumatic Gravity. Here we have an additional degree of freedom that is phi, that comes as with some derivative operators, and also with this x, that is the kinetic part of the scalar field. It's the kinetic energy. But then, if you look at this, we have another field that is this lambda, that's called the pneumatic field, that comes in only here. So there are no derivatives, and this means that this acts into this Lagrange as a Lagrange multiplier. So it fixes this object here to be equal to 0. And so doing this calculation that is very easy to do, we find this so-called mimetic constraint that fixes the field to be equal to time at any time. And what we have, the freedom that we have in this model is to choose the action parameter alpha, gamma, and beta. But the main freedom comes from the choice of this potential. So if we choose a functional form of this potential that again is a function of time because the field is time, we can choose what we want to mimic with this modified gravity model. And then we have the standard cosmological matter that comes here, minimally coupled with the metric. So there is no coupling with the new degrees of freedom and the matter. And if we develop this theory, what we find are the equations, so the background equations, so the first step in our list. And what we find are equations that are really similar to the one that we have in general relativity, where we added this term here. So we have a new row TF and PDF, that stands for dark fluid. And the density is given by this. And here you can see that we have a part, the first part that is related to how to model dark matter. And then we have another part that, depending on the choice of the potential, it can mimic dark energy more or less as in lambda CDM, depending on the choice of the potential. And another feature of this model is that here you have something that in a way changes the cosmological constant in an effective way. Because depending on the choice of the parameter that are constant, we can get something that is different from general relativity. So it just creates an effective cosmological constant. Sorry, an effective gravitational constant. And we can develop this equation, and we included it into the I class to include this new mimetic model. And what we found are these plots like this. So here you see the fractional densities. These are the densities of one component, for instance, baryon, the dark fluid, or the radiation, divided by the total density. And in time, you can see that they basically overlap with lambda CDM, because you are supposed also to see the dashed lines that are completely overlapping with the continuous ones that are from our model. And here you can see exactly that this is lambda CDM behavior. Why it is so? Because if we look at the equation of state parameter, which is the pressure divided by the density at each time, we get something that is 0, so pressureless fluid, like dark matter, and then it goes to -1, so something that is more like dark energy. But then we have the second step in our list, that is to look at the linear perturbations. And two quantities that we should check are these velocities of the scalar perturbations and the velocity of the gravitational waves. And for this, in particular, we have that from LIGO Virgo experiments, this object is constrained to be equal to the speed of light up to some error. Our question was, how much small should beta be? Because if you check this, it seems like this should be 0 in order to keep very short one. There's someone talking. Okay. And why do we want to check the smallness of beta? Because this kind of, I mean, the object that we add to the action might have some meaning as quantum correction. So we might also want to check if these parameters can be non-zero and very small. And the way to do this is with another numerical method that is called Bayesian analysis. So what we can do is to actually find the values in a probabilistic way. So we use as a likelihood the CT square equal to 1, and then we put our priors in the values of the CS square, so the scalar perturbation velocity and the tensor perturbations velocity. This is a very simple example because the likelihood is composed by only one data, the CT square equal to 1. And without going into the details of the results that we have here, what I wanted to show is that in order to arrive there, what we have to do was to start from the Lagrangian, derive all the equation that might be more or less complex depending on the model. And then we had to modify the Boltzmann code in order to find the equation of motion. And then we had also to modify the NCNC code in order to include our model. So it was a bit of a long journey. So the question here is, can we do something that is more model independent? So if, because if you check our list, what we did up to now was just this part and part of this. This was already a long work. The answer is yes, we can do this in a model independent way. And one proposal, one alternative is to use this so-called theory of dark, effective field theory of dark energy. This monster action includes all the correction to GR, in the sense that it includes all the possible correction that we might have if we include one additional scalar degree of freedom to the theory. And here is up to the second order. All these functions that you see here that are function of time can be mapped to a covariant model like the one of the pneumatic gravity, for instance. What is the drawback of using something like this is that all these terms are more difficult to interpret physically because we don't know exactly what these terms are doing singularly to the physics of the system. So I want to have both pictures in mind. And what can be done, for instance, is to check, is to constrain these functions here that are, again, function of time with data. Then we map our modified gravity model into these functions. So we map whatever model, like the pneumatic gravity model into the function that you see here in this action. And then we compare to check if our model is viable, but we do the part related to constraining the with data just once with this. For instance, let me give you an example of this mapping. Consider this model here. This is a model, this is a Nordesky model. It means that it has at most equation of motion at second order. So no higher derivatives that might lead to some instabilities. And this example is nice for what I'll show you in a second. It's because we have a non-trivial analytical solution for the scalar field. You get this, where Q is a integration constant and alpha and zeta are the parameters of the action. And so what we can do is to find the mapping between the function that I showed you before. So these are actually function of time because we have, again, the exact solution for this phi here. So sorry, for this psi here. And all the other functions are null in this case. And what we can check if they actually agree with these pictures. So if we do the two calculations with EFT-CAM and I-class, we find that they're very similar. I think that the small differences here that you see are related to the fact that they use different numerical schemes. So at the background level, for instance, this model is very nice. This omega p is our field. It's very nice in mimicking dark matter. While dark energy is the red one, is going to be dominant at light times. It's the one of lambda CDM, so the standard one. But then what we also have to check again are the perturbations. So for instance, here we have the CS squared, so the velocity of the scalar perturbations. As if you know something about modified gravity, you know that this means since we have some negative values here and also at late times, that we will find some instabilities. And indeed, if we check our results for the matter power spectrum, we find that it's completely unstable. But what is important here is that both I-class and EFT-CAM, so both approaches, gave us the same stability results. So it means that we can do this once for each decay. Find the values of the functions that are not allowed, that gives us instabilities like this once, and then we can just say if our model is unstable or not without modifying again another Boltzmann code to do the same kind of analysis. But then there are also other methods that are, let's say, more model independent. This is, for instance, a parameterization method that is used for n-body simulations, and in particular for the nonlinear structure progression. This was a proposal that was relatively recent to modify the gravitational constant in this way. Here you can see that we have a lot of free constant parameters like this A, capital B, small b, R0, and small a, that can be used to include the modification of gravity given by our modified gravity model into an effective cosmological constant. This was already studied in the large-scale regime part. What we are doing with Marco is try to extend this to a code called Gadget, where we also have the small-scale part. For those who know Gadget, this means that the PM part is already implemented like they did in the previous job. But then here, what we are doing is to implement the three parts, so the part at small scale. Here you can see a model of NDGP and the boost given by our modified gravity model, so the difference with respect to GR results. Here you can see that we get something that is, we have a boost on our power spectrum. And this is a preliminary result, so the error are not the best. We have a 2.5% difference between the orange one that is supposed to be an exact simulation, so where we solve the new degree of freedom on the grid, so exactly, while our case is with the parameterization. But the question here that might arise is, why do we do this? We already have the exact simulation, so why are we doing this? Well, the fact is that this kind of parameterization is way faster than what can happen in an exact simulation, because in exact simulation, again, you have to solve the new degrees of freedom on the grid, and you have to, and this can be really, really slow. While in our case, we have running times that compared to lambda CDM are essentially the same, more or less 10%, so really nothing. And maybe the second reason why it might be interesting to use them is reverting the reasoning. So in the sense, we can just use this in a model independent way. So compute this function for, and the modification given by this for different parameters. And then we check if our model that we map into this object here, to these constant parameters, are actually in agreement with data. So let me draw some conclusion. What I wanted to show you, and I hope I did it, is that we have several methods to approach modified gravity. One of these is use Bayesian inference for parameter estimation. There are also other methods in Bayesian analysis that are completely not mentioned here, like, for instance, model comparison, that are also useful. And then I also showed that maybe there are some model independent approach that can be used in order to make this comparison with data more efficient. And then I also showed that there are some parameterization methods that can be used on n-body simulation to speed up our simulation, but also as another example of a model independent approach. So thank you for your attention.
Okay, thank you very much.